In a previous video, we looked at the properties of roots of quadratic equations. In this video, we are going to extend our results to look at the roots of cubic equations. Initially, we just want a little bit of preliminary algebra. We already know that x plus y all squared is equal to x squared plus 2xy plus y squared. And in the previous video, we made use of the fact that that enabled us to say that x squared plus y squared is equal to x plus y all squared, take away 2xy. If we now consider x plus y plus z all squared, we know that that means x plus y plus z times by x plus y plus z. And if we multiply the brackets out carefully, we'll get x squared plus xy plus xz plus yx plus y squared plus yz plus zx plus zy plus z squared. And if we tidy it up, we see we've got x squared plus y squared plus z squared plus 2 lots of xy, 2 lots of xz and 2 lots of yz. And that means that we can say that x squared plus y squared plus z squared is equal to x plus y plus z all squared, take away 2 lots of xy plus xz plus yz. Now we'll be using this result quite a lot later on during the course of this video. We'll now move on and start considering some cubic equations. Now these days we're lucky enough to have calculators, many of which will solve cubic equations for us. So we've got here 5 different cubic equations, and I've used my calculator to obtain the roots, which we're going to call alpha, beta and gamma, of those 5 equations. And what I want to do is investigate the properties of alpha plus beta plus gamma, then of alpha beta plus beta gamma plus gamma alpha, and then finally of alpha times beta times gamma. So, for alpha plus beta plus gamma, we simply need to add the 3 roots up. So in the first case, we're going to have 2 plus 1 plus minus 4, which gives me minus 1. The second case, we're going to have 3 plus 3 plus 2, which gives me 8, and so on. So, we've got, for the first equation, alpha plus beta plus gamma is minus 1. The second equation, alpha plus beta plus gamma is 8. The third equation, we've got alpha plus beta plus gamma is minus 0.5. The fourth equation, we've got alpha plus beta plus gamma is 1.5. And for the fifth equation, we've got alpha plus beta plus gamma is 3. Now, can you see any connection between the values of alpha plus beta plus gamma and the coefficients of the original equations? In the first equation, we can see that the coefficient of x cubed is 1 and the coefficient of x squared is also 1. Alpha plus beta plus gamma is minus 1. In the second equation, we can see that the coefficient of x cubed is 1, coefficient of x squared is minus 8, and the value of alpha plus beta plus gamma is 8. And in the third equation, we can see that the coefficient of x cubed is 2, the coefficient of x squared is 1, and the value of alpha plus beta plus gamma is minus 0.5. See whether you can determine the pattern for alpha plus beta plus gamma and how it is linked to the coefficient of x cubed and the coefficient of x squared. Then see whether you can find a connection between the values of alpha beta plus beta gamma plus gamma alpha and the coefficients in the equation. And finally, see whether you can find a relationship between the value of alpha, beta, gamma and the coefficients inside the original equations. Just pause the video while you do that, see whether you can find that relationship, and then once you've done that, continue watching the video. Okay, let's suppose that we've got a cubic equation ax cubed plus bx squared plus cx plus d equals 0, and that it's got roots alpha, beta and gamma. Then the factor theorem tells us that we must have factors of x minus alpha, x minus beta and x minus gamma. So we've got ax cubed plus bx squared plus cx plus d must equal x minus alpha times x minus beta times x minus gamma. But if I just have x minus alpha, x minus beta, x minus gamma, I'm just going to have a single x cubed on the right hand side and a lots of x cubed on the left hand side. So to get the x cubed terms balancing on each side of our identity, we need to have a factor of a in front of the x minus alpha, x minus beta, x minus gamma. So we've got ax cubed plus bx squared plus cx plus d must equal a times x minus alpha, x minus beta, x minus gamma. We can multiply out the right hand side. So the sensible thing might be just to multiply out x minus alpha, x minus beta first of all and leave the x minus gamma untouched. So if I do that, the right hand side just becomes a times by, first of all, x squared minus alpha plus beta x plus alpha beta, and also multiplied by x minus gamma. Multiplying out the brackets on the right hand side now gives us a times by x cubed minus gamma x squared minus alpha plus beta lots of x squared plus alpha plus beta times gamma x plus alpha beta x minus alpha beta gamma. And if we collect together the x cubed terms, the x squared terms, the x terms and the constant term separately, then we've got a times by x cubed minus alpha plus beta plus gamma lots of x squared plus alpha beta plus beta gamma plus gamma alpha lots of x minus alpha plus beta plus gamma. And finally we multiply the big bracket on the right hand side out by a and obtain on the left hand side ax cubed plus bx squared plus cx plus d, and on the right hand side we've got a lots of x cubed minus a times alpha plus beta plus gamma times x squared plus a times alpha beta plus beta gamma plus gamma alpha lots of x minus a times alpha beta gamma. So if we compare the coefficients, first of all the coefficient of the x squareds, we're going to have b must equal minus a times alpha plus beta plus gamma. Comparing the coefficients of x, we've got c must equal a times alpha beta plus beta gamma plus gamma alpha. And then the constant term at the end of each side, we've got d on the left hand side must equal minus a alpha beta gamma. Now if we divide these expressions through, in the first case by minus a, we will get minus b over a equals alpha plus beta plus gamma. If we now divide each side of the second equation by a, we get c over a equals alpha beta plus alpha gamma plus beta gamma. And if we divide each side of the third equation by minus a, then we get minus d over a equals alpha beta gamma. And these three results are going to be very important as we deal with questions involving cubic equations. So in our first example, we've got the equation 2x cubed plus 7x squared minus 5x minus 1 equals 0, which has got roots alpha, beta and gamma. And we're being asked to find the value of alpha plus beta plus gamma. 1 over alpha plus 1 over beta plus 1 over gamma, alpha squared plus beta squared plus gamma squared, and finally alpha cubed plus beta cubed plus gamma cubed. Now, from what we've just done, we know that alpha plus beta plus gamma is always equal to minus b over a, so in this case here it's minus 7 over 2. Now it's worth writing down at this stage, before we go any further, the other two results that we can write down straight away. The second result is that alpha beta plus alpha gamma plus beta gamma must equal c upon a, which in this case is minus 5 over 2. And we've got alpha times beta times gamma must equal minus d upon a, which in this case is minus 1 over 2, so that gives me a half. So for part B, we have to work out 1 over alpha plus 1 over beta plus 1 over gamma. We've got a common denominator there for 1 over alpha plus 1 over beta plus 1 over gamma of alpha beta gamma. 1 over alpha is the same thing as beta gamma over alpha beta gamma. 1 over beta is the same thing as alpha gamma over alpha beta gamma. And 1 over gamma is the same thing as alpha beta over alpha beta gamma. And what we've got there is we know that the denominator, alpha beta gamma, is a half, but we know that beta gamma plus alpha beta is exactly the same thing as alpha beta plus alpha gamma plus beta gamma, so that's minus 5 over 2. So we've got a numerator of minus 5 over 2, denominator of a half, so that gives me minus 5. For part C, we're going to use that result we pointed out right at the beginning of this video, that alpha squared plus beta squared plus gamma squared is the same thing as alpha plus beta plus gamma all squared. Take away 2 lots of alpha beta plus alpha gamma plus beta gamma. In other words, it is minus 7 over 2 squared. Take away 2 times minus 5 over 2. So that is 49 over 4 plus 5, which gives me 69 over 4. Now for part D, it would be tempting to try and do something similar to what we did in part C. To say that alpha cubed plus beta cubed plus gamma cubed is the same thing as alpha plus beta plus gamma all cubed, but then minus some terms to make the expression correct. The problem with this is the algebra involved with finding what those unknown terms are is horrendous. It's not a route we want to go down. A much easier way of finding out the value of alpha cubed plus beta cubed plus gamma cubed is to remember that we know that alpha is a root of the equation 2x cubed plus 7x squared minus 5x minus 1 equals 0. So we know that 2 alpha cubed plus 7 alpha squared minus 5 alpha minus 1 must equal 0. And the same is true for 2 beta cubed plus 7 beta squared minus 5 beta minus 1. That must equal 0. And 2 gamma cubed plus 7 gamma squared minus 5 gamma minus 1 must also equal 0, because beta is the root of the equation and gamma is the root of the equation. If we add up these three equations that we've got, then we're going to obtain 2 lots of alpha cubed plus beta cubed plus gamma cubed, plus 7 lots of alpha squared plus beta squared plus gamma squared, minus 5 lots of alpha plus beta plus gamma minus 3 must equal 0. So we know the value of alpha squared plus beta squared plus gamma squared. We know the value of alpha plus beta plus gamma. So we can now say that we have got 2 lots of alpha cubed plus beta cubed plus gamma cubed plus 7 times 69 over 4 minus 5 times minus 7 over 2 minus 3 must equal 0. Tidying that up, we've got 2 lots of alpha cubed plus beta cubed plus gamma cubed, add 541 divided by 4 must equal 0, from which we can easily deduce that alpha cubed plus beta cubed plus gamma cubed must be minus 541 divided by 8. For our second example, we're going to have the equation x cubed plus 4x squared minus 7x minus 6 equals 0, and we're told that this has got roots of alpha, beta and gamma. And we have to find a cubic equation with integer coefficients whose roots are 2 alpha plus 1, 2 beta plus 1 and 2 gamma plus 1. Now we're going to look at 2 different solution methods for this example. I know which one I think is the simplest, but I'm going to leave you to decide that yourself. So the first solution, what we're going to say is, alright, we know first of all that the values of alpha, beta and gamma satisfy alpha plus beta plus gamma must be minus b over a, which in this case gives me minus 4. Alpha beta plus alpha gamma plus beta gamma must be c upon a, which in this case is minus 7 over 1, or minus 7. And finally, alpha beta gamma must be minus d upon a, which in this case is minus 6 upon 1, which gives me 6. Now I'm going to suppose that the equation ax cubed plus bx squared plus cx plus d equals 0 has got roots 2 alpha plus 1, 2 beta plus 1 and 2 gamma plus 1. Then, making use of my fundamental results, first of all I know that the sum of the roots, so that is the value of 2 alpha plus 1 plus 2 beta plus 1 plus 2 gamma plus 1 must be minus b over a. In other words, I've got 2 lots of alpha plus beta plus gamma, add 3, must give me minus b over a. But I know that alpha plus beta plus gamma is minus 4. So I've got minus b over a, must be 2 times minus 4, add 3. In other words, minus b over a is minus 5, which tells me that b must be equal to 5a. Now we can do a similar sort of argument to find the values of c and d in terms of a. We know that the first root times the second root plus the first root times the third root plus the second root times the third root will give me the value of c upon a. So 2 alpha plus 1 times 2 beta plus 1, add 2 alpha plus 1 times 2 gamma plus 1, add 2 beta plus 1 times by 2 gamma plus 1 must give me the value of c upon a. A little bit of algebra to multiply this out now. We get c upon a equals 4 alpha beta plus 2 alpha plus 2 beta plus 1. That's the result of multiplying out the 2 alpha plus 1 by the 2 beta plus 1. Plus also 4 alpha gamma plus 2 alpha plus 2 gamma plus 1. Plus also 4 beta gamma plus 2 beta plus 2 gamma plus 1. Now the right hand side can be rewritten as 4 lots of alpha beta plus alpha gamma plus beta gamma plus 4 lots of alpha plus beta plus gamma plus 3. We know that alpha beta plus alpha gamma plus beta gamma is minus 7. We know that alpha plus beta plus gamma is minus 4. So we've got 4 times minus 7 plus 4 times minus 4, add 3, and that gives me minus 41. So we've got C must equal minus 41A. Finally, we know that the first root times by the second root times by the third root must equal minus D upon A. So we've got 2 alpha plus 1 times by 2 beta plus 1 times by 2 gamma plus 1 must equal minus D upon A. We already know that 2 alpha plus 1 times 2 beta plus 1 is 4 alpha beta plus 2 alpha plus 2 beta plus 1. So we've got minus D upon A is 4 alpha beta plus 2 alpha plus 2 beta plus 1 times 2 gamma plus 1, which multiplies out to give me 8 alpha beta gamma plus 4 alpha beta plus 4 alpha gamma plus 2 alpha plus 4 beta gamma plus 2 beta plus 2 gamma plus 1. So what we've got there is we've got 8 lots of alpha beta gamma plus 4 lots of alpha beta plus alpha gamma plus beta gamma plus 2 lots of alpha plus beta plus gamma plus 1. So we know that minus D over A is 8 times 6 plus 4 times minus 7 plus 2 times minus 4, add 1. So I've got minus D over A must equal 13. In other words, D must be equal to minus 13A. So the equation that I've got, which was ax cubed plus bx squared plus cx plus d equals 0, can now be rewritten as ax cubed plus 5ax squared minus 41ax minus 13a equals 0. And if we let a equal 1, then we get the cubic equation x cubed plus 5x squared minus 41x minus 13 equals 0 is the equation which is going to have roots 2 alpha plus 1, 2 beta plus 1 and 2 gamma plus 1. Now there's a lot of algebra in that. There is a different way of doing it which reduces the algebra possibly by as much as 50%. Let's have a look at what the second solution method is. What we're going to do is I'm going to start off by saying let y equal 2x plus 1, because that's the original equation has got solutions x equals alpha, x equals beta, x equals gamma. I want to find an equation with roots which are 2 times the original x value, add 1, 2 times the original root plus 1. So I'm going to let y equal 2x plus 1 for a moment. If I let y equal 2x plus 1, that is exactly the same thing as saying that x is y minus 1 divided by 2. So I'm going to transfer the statement in blue, which is a statement about x, into a statement about y. So I can do that by simply substituting y minus 1 over 2 every time x appears in the blue line. So I've got y minus 1 over 2 cubed plus 4 lots of y minus 1 over 2 squared minus 7 lots of y minus 1 over 2, take away 6 equals 0, has roots of y minus 1 over 2 equals alpha, beta or gamma. Y minus 1 over 2 cubed is the same thing as y minus 1 cubed over 8. Similarly, y minus 1 over 2 squared is the same thing as y minus 1 squared over 4. So the equation can be rewritten as y minus 1 cubed over 8 plus 4 lots of y minus 1 squared divided by 4 plus minus 7 lots of y minus 1 over 2, take away 6 equals 0, has roots, and I've gone back now. The fact I know y minus 1 over 2 equals alpha, beta or gamma means that I know y must equal 2 alpha plus 1 or 2 beta plus 1 or 2 gamma plus 1. The fractions are a little bit nasty in the equation, so it would be a good idea just to multiply straight through by 8, which will give me a rather easy equation, and the easy equation is y minus 1 cubed plus 8 lots of y minus 1 squared. Take away 28 lots of y minus 1. Take away 48 must equal 0. And now I need to use Pascal's triangle to expand y minus 1 cubed. And if I use Pascal's triangle to expand y minus 1 cubed, I get y cubed minus 3y squared plus 3y minus 1. Then I've got 8 lots of y squared minus 2y plus 1. Take away 28 lots of y minus 1. Take away 48 equals 0. Now if I look at the terms here, starting off with the y cubed, there's simply one y cubed. Looking at the y squareds that I've got minus 3y squared in the first bracket, but plus 8y squared from the second bracket. So that's going to give me plus 5y squared. Looking at the y terms, I've got 3y in the first bracket, I've got minus 16y from the second bracket, and I've got minus 28y from the third bracket. So that's going to give me 3, take away 16, take away 28, take away 28, which gives me minus 41y. Finally, looking at the constant terms, I've got minus 1 from the first bracket, plus 8 from the second bracket, plus 28 from the third one, and then I've got the minus 48 as well at the end, and that altogether gives me minus 1 plus 8 plus 28, take away 48, so that is minus 13. So my left-hand side simplifies to y cubed plus 5y squared minus 41y minus 13 equals 0. And that is the equation which has roots y equals 2 alpha plus 1, 2 beta plus 1, 2 gamma plus 1. At this stage, I'd just like you to pause the video and try answering a similar question using either of the two methods just introduced. So pause the video, answer the question, and then when you restart, the final answer will appear there for you to check. And then we'll go on and we'll have a look at what happens if we deal with quartic equations. So there's the final answer for this question. Really doesn't matter whether you use x's or y's in these questions, it's the coefficients that really matter at this point. For our final example, we have the equation ax cubed plus bx squared plus cx plus d equals 0, which we are told has roots of alpha, alpha and 4 alpha. And we have to prove that 2bc minus 27ad has to equal 0. Well, we know that the sum of the roots is always equal to minus b over a. So in this case, we know that alpha plus 4 alpha must equal minus b over a. In other words, we've got 6 alpha must equal minus b over a. We also know that the first root times the second root plus the first root times the third root plus the second root times the third root is always equal to c upon a. So in this case, we have got alpha times alpha plus alpha times 4 alpha plus alpha times 4 alpha must equal c upon a. And that simplifies through to give me 9 alpha squared equals c upon a. Finally, we also know that the product of the three roots, so that's the first root times the second root times the third root, is always equal to minus d upon a. So in this case we've got alpha times 4 alpha must equal minus d upon a, or 4 alpha cubed is minus d upon a. Now equation 1 tells me that b is minus 6a alpha. Equation 2 tells me that c is 9a alpha squared. And equation 3 tells me that d is minus 4a alpha cubed. So 2bc minus 27ad is 2 times minus 6a alpha times by 9a alpha squared. Take away 27 times by a times by minus 4a alpha cubed, which simplifies to minus 108a squared alpha cubed plus 108a squared alpha cubed, and that gives me 0 as required. So that concludes our video on the properties of roots of cubic equations.